Today we've got a nice number theory problem from the 2023 Asia-Pacific Math Olympiad. So let's dive right in. So let's maybe recall first this sum of all divisors of n function, which we'll denote by sigma of n. And then for the purposes of this video, we'll say that p of n is the largest prime divisor of n. And then our goal is to determine all integers n that are bigger than or equal to 2, satisfying this condition right here. We have n equals sigma of n sigma of n over p of n minus 1. But let's quickly observe that that's equivalent to the following equation. We have sigma of n over n is equal to p of n minus 1. And actually, that's the version that we want to work with. That's because this right-hand side is kind of a more natural shape or a natural object than this right-hand side over here. Okay, so the first thing that I'd like to do is look at a question which is maybe a simplification of this problem, and that is, can we have n is just a power of a prime? And so I think maybe if we can solve this question, that'll give us some sort of motivation for how to proceed with the question generally. Okay, so let's look at this question. So notice that here we kind of pretty clearly have p of n is equal to p. That's because we only have a single prime divisor. So the largest prime divisor is whatever that is. And so we also have sigma of n is equal to 1 plus p squared all the way up to p to the m. That is all divisors. So all divisors will be the powers of the primes from p to the 0 up to p to the m. But notice that this is a finite geometric series, so we can sum this up to p to the m plus 1 minus 1 over p minus 1. So we've got something like that. All right, cool. So now let's look at our equation right here and write our equation using those parts. So notice that p of n minus 1 will simply be p minus 1. And then we'll have sigma of n, which is p to the m plus 1 minus 1 over p minus 1 over p minus 1. But then I have to divide by n as well. So dividing by n will simply give me a p to the m here. Okay, so nothing fancy's really happened yet. But now let's observe that I can maybe write this as p minus 1 quantity squared equals, and so we'll have p minus 1 over p to the m. So that's what I get simply from multiplying this p minus 1 over to the left-hand side. And then after that, I'm dividing both terms in the numerator by this p to the m. Okay, cool. But now let's see what we've got here. Let's multiply out this left-hand side, and we'll have p squared minus 2 times p plus 1 is equal to p minus this 1 over p to the m. But then moving this p over to the left-hand side gives me a quadratic inequality. I have p squared minus 3 times p plus 1 is equal to 1 over p to the m, or minus 1 over p to the m, which itself is less than 0. But now, since this is a quadratic expression that's less than 0, we know that this inequality occurs exactly between the two roots of this equation. So let's find the solutions to, let's see, x squared minus 3x plus 1 equals 0. But notice that doesn't factor nicely, so we'll have to use the quadratic equation. So let's see, we'll get x equals 3 plus minus the square root of, well, the b squared, so that's going to be 9 minus 4 times a times c, so that's going to be minus 4 all over 2. So let's observe that that's 3 plus minus the square root of 5 over 2. So like I said, the places where this quadratic inequality is satisfied is between those two roots. So that means that we have p is less than 3 plus root 5 over 2, and it is greater than 3 minus root 5 over 2. Now, we're going to show that that's going to be problematic. So let's see, the square root of 5 is going to be a little bit less than 2. So that means over here on this side of the inequality, we can replace the square root of 5 with the square root of 4, or 2, and push the inequality in the same direction. So that's going to give us 3 plus 2 over 2. In other words, it's going to be 5 over 2. But let's see, that's like 2.5. So if we have this prime p, which is less than 2.5, that means that p has to be equal to 2. So in other words, if we can solve our equation over here with a simple power of a prime, it means that that prime has to be the prime 2. So let's loop that back into this equation right here and see if everything works out. So we've got 2 minus 1 squared, so that's going to be 1. So here we have 1 is equal to 2 minus 1 over 2 to the m. But observe that that only occurs if m is equal to 0. But if m is equal to 0, then we get n is equal to 1, which is in contradiction to this right here. Okay, so that means that there are no solutions to our equation where our n is a power of a prime. Okay, so now that we've done this warm-up version of our problem, let's jump into the problem as a whole. Okay, so we just finished showing that n must have more than one prime factor. Now, we didn't phrase it like that, but that is the upshot of what we just did during our warm-up. Okay, so now let's write n as p1 to the m1 times p2 to the m2 all the way up to pk to the mk. So in other words, our prime factors are p1 up to pk, and they have the exponents m1 up to mk. But now let's observe, we might as well say that we have an ordering here where p1 is less than p2, all the way up is less than pk, meaning that our p of n is equal to p sub k, because that's the largest prime factor or prime divisor of our number n. Okay, so now let's calculate the sigma of n function, but let's observe that that's going to be k sums, where we're summing over all possible powers of p to the 1 and p to the 2 and so on and so forth. So we could write that in the following way. So we've got the sum as j1 goes from 0 up to m1, and then inside of that the sum as j2 goes from 0 up to m2, and so on and so forth, up to the sum as jk goes from 0 up to mk of p1 to the j1 times p2 to the j2 all the way up to pk to the jk. Okay, nice. So that sums over all possible numbers where the prime factors are p1 to pk, and you can take any powers from 0 to the maximum possible power, which is m1, m2, mk, so on and so forth. Okay, nice. But now what we can do is split this up into a product of k sums. So we've got the sum as j goes from 0 to m1 of p1 to the j1 times the sum as j2 goes from 0 to m2 of p2 to the j2 all the way up the sum as jk goes from 0 up to mk of pk to the jk. So that's just factoring that multi-sum out into a product of a bunch of single sums. But now we can apply the sum of a finite geometric series rule to each of these, like we did to our single prime power before. So that's going to give me here a p1 to the m1 plus 1 minus 1 over p1 minus 1. And then this next term will be a p2 to the m2 plus 1 minus 1 over p2 minus 1. And then this last one will be a pk to the mk plus 1 minus 1 over pk minus 1. So we've got that is our sigma of n. So let's observe, that means our sigma of n over n can be written as follows. So I think maybe the best way to write this is as p1 to the m1 plus 1 minus 1 over p1 to the m1 times p1 minus 1. And then a similar term for p2 all the way up to pk to the mk plus 1 minus 1 over pk to the mk times pk minus 1. So I just slotted in all of its prime factors into each of these kind of natural places in our product which existed for this sigma of n. But now what I can do is replace this equality here with an inequality if I just take away these minus 1s. That's because I'm making the numerator bigger, which is going to push the whole thing bigger. But now observe that I get a numerator and a denominator cancellation. So this m1 plus 1 and this m1 will cancel each other down. And then this mk and then this mk plus 1 will cancel each other down as well. So that gives me sigma of n over n is less than or equal to this product, which is P1 over P1 minus 1 times P2 over P2 minus 1 all the way up to PK over PK minus 1. Okay, so now that we've got that all in order, let's use this inequality to start the rest of our argument on the next board. Okay, so let's see where we ended up. We've got this P of n minus 1 is P sub k minus 1 because P sub k was our largest prime factor. But then our equation is that this P of n minus 1 is equal to sigma of n over n. And we just built an inequality showing that this sigma of n over n is less than or equal to this product, P1 over P1 minus 1 times P2 over P2 minus 1 all the way up to PK over PK minus 1. Now, I'd like to do a step which is only possible if PK is bigger than or equal to 5. Now you might say, well, why should we do that step? And that's because we'll see that this step will lead us to some sort of contradiction, meaning that our largest prime cannot be bigger than or equal to 5. Okay, so let's just put right here that if PK is bigger than or equal to 5, we can do the following step. And that is, well, we can replace this with 2 over 2 minus 1, which is 1, times 3 over 3 minus 1, which is 3 over 2, times 5 over 4, times 7 over 6, times 9 over 8, all the way up to pk minus 2 over pk minus 3 times pk over pk minus 1. So what did I do there? Well, I took my product and then I slotted between all of these primes all possible odd numbers in the numerator and one less than the odd numbers in the denominator. And so that's going to give me this product, which is 2 over 1, and then observe after that I have 3 times 5 times 7 times 9 times 11 times 13, all the way up pk minus 2 times pk over 2 times 4 times 6 times 8, all the way up to pk minus 3 times pk minus 1. So this is going to be the product of all odds up to pk, and then all evens up to pk minus 1. And that pretty clearly gives me something that's larger because I'm just including more terms in my product that are bigger than 1. Now, the next thing that I want to do is take this 1 which is in the denominator, realize that it doesn't do anything, and then move all the denominators over one step. So that's not going to change what this is equal to, but it's going to leave me with 2 over 2 times 3 over 4 times 5 over 6 times 7 over 8, all the way up to pk minus 2 over pk minus 1 times pk, maybe over 1, although I don't really need to write that. But now observe what I'm left with. This 2 over 2 is equal to 1. And then all of this stuff in the lead up to the last terms are all less than 1. So that builds me this inequality where this whole thing is less than pk times pk minus 2 over pk minus 1. But now we're going to see that that's problematic. I'm going to multiply that out, and I'm going to get pk squared minus 2 times pk over pk minus 1. But now what I'll do is I'll add 1 to the numerator, and that's going to create something larger. So I've got this inequality. This is bigger than pk squared minus 2 times pk plus 1 over pk plus 1. But now let's observe that I can factor that numerator. That should have been a pk minus 1. and I factor that numerator as pk minus 1 squared, and then I've got that's over pk minus 1, and then this whole thing is equal to pk minus 1. But now if we take a step back, let's observe that we've just created a contradiction. Because over here at the extreme left-hand side, we have a pk minus 1. At the extreme right-hand side, we also have a pk minus 1. And then in the middle, we have a strict inequality. But obviously, something cannot be strictly less than itself. So that means that somewhere we've made a choice which led to a contradiction, and that choice is right here where we assumed that our largest prime was bigger than or equal to 5. But that means our largest prime has to be strictly less than 5. But that means that our number n is simply of the form 2 to the a times 3 to the b. That's going to be the product of all primes smaller than 5 with, some exponents there. And then let's observe also that a and b are strictly bigger than 0. And that's because if one of them is equal to 0, then n has exactly one prime factor, but we already showed in our warm-up that n has strictly more than one prime factor. So, well, that's a good place to be. Notice we've got n is equal to 2 to the a times 3 to the b. A and b are both bigger than 0. So I think that puts us into a pretty good spot to finish this thing off. All right, so everything we've done so far has led us to n being of the form 2 to the a times 3 to the b, where a and b are bigger than or equal to 1. Now our original equation has the following form. So we've got 2, that's equal to 3 minus 1, which is this p of n minus 1. The largest prime here is 3. And then this sigma of n over n, just specializing our formula from the previous board, is 2 to the a plus 1 minus 1 over 2 to the a times 2 minus 1, and then 3 to the b plus 1 minus 1 over 3 to the b times 3 minus 1. But now, obviously, 2 minus 1 is simply 1, so we can just kind of forget about that. 3 minus 1 is equal to 2, so we can replace that with a 2. But now what we can do is move some things around. Notice that I can multiply that 2 from the denominator up to the numerator to give me a 4. And then I can do this quotient. So 2 to the a plus 1 over 2 is going to be 2 minus 1 over 2 to the a. And then here we have, 3 minus 1 over 3 to the b. So we've got this equation right here. And now I'm going to speculate that not only is a bigger than or equal to 1, but it has to be equal to 1. And I'm going to prove that's the case by supposing that a is bigger than or equal to 2 and showing that we get a contradiction from that. So let's do this right here. So let's suppose that a is bigger than or equal to 2, and let's see where that gives us some sort of problem. So let's take this equation that we've got. So we've got this 4 is equal to 2 minus 1 over 2 to the a times 3 minus 1 over 3 to the b. But now if a is bigger than or equal to 2, that means that this object right here is going to be bigger than or equal to 2 minus 1/4. You might say, well, it's in the denominator there, so shouldn't it be a less than symbol? But then we've got a minus sign there too, so the inequality gets switched 2 different ways. So let's see, this is going to be bigger than or equal to 2 minus 1/4, like I said, and then times 3 minus 1 over 3 to the b. But we can do a little calculation here. 2 minus 1/4 is going to be 7 over 4. And then here we have 3 minus 1 over 3 to the b. So we've got something like that. But now let's observe that moving some things around, that gives us the inequality 3 minus 1 over 3 to the a is less than or equal to 16 over 7. But now, since a is bigger than or equal to 1, we know that this 3 minus 3 to the a is bigger than or equal to 3 minus 1/3. But 3 minus 1/3, let's see, that's going to be 9/3 minus 1/3. That's going to be 8 over 3. But now we can divide both sides by 8 here, and we'll see that that means that 1/3 is less than or equal to 2 over 7. But observe, that means that 7 is less than or equal to 6, so that pretty clearly gives us a contradiction. We obviously had a contradiction at this line right here, but it's nice to take it all the way just to see how absurd this is. Okay, so just like as a reminder, that's a contradiction that A is bigger than or equal to 2, meaning A must be equal to 1. And that means that our number here is really of the form 2 times 3 to the b, where b is bigger than or equal to 1. Okay, so now let's see what we can do with that. Okay, so we got this down to our numbers of the form 2 times 3 to the b, where b is bigger than or equal to 1, and now we're ready for the final calculation. So this is our original equation now. We've got 2 is equal to 4 minus 1 over 2 times 3 to the b plus 1 minus 1 over 2 times 3 to the b. So let's observe that I can take these 2's and multiply them up here. So that's going to give me like 8 equals, and then this is going to be 3 times 3 to the b plus 1 minus 1 over 3 to the b. So 4 minus 1 is kind of obviously equal to 3. But now let's observe that we can write that as 3 to the b plus 2 over 3 to the b. So that's going to be 9 minus, and then we've got 3 over 3 to the b. So that's going to be 1 over 3 to the b minus 1. But now let's observe that this is going to be bigger than 8 as long as b minus 1 is strictly bigger than 0. That's because we're subtracting from 9 something that is less than 1. But that means that b minus 1 has to be equal to 0. In other words, b is equal to 1. But then if b is equal to 1, we have our final number, and that's 2 to the 1 times 3 to the 1. In other words, we have the number 6. And that's a good place to stop.